In this video, we're going to do an example problem which puts together two different concepts that we learned in class. We're going to put together rolling motion and rotational kinetic energy. In class, we learned that if we have an object rolling without slipping, then we can think about that rolling motion as a combination of an overall translation of the center of mass combined with a rotation about the center of mass. In order for the object to be truly rolling without slipping, the relation between these two would be that the center of mass speed is equal to the angular velocity times the radius of the object. In class, we also saw a couple of different formulas that we can use to calculate rotational kinetic energy. If we have an object rotating around a fixed axis, then the kinetic energy of the object is equal to 1/2 moment of inertia with respect to the fixed axis times angular velocity squared. However, we do not always have a fixed axis, so we have a more general formula which breaks down the kinetic energy as one term associated with the overall translational motion plus a second term which is associated with the rotation of the object around the center of mass. So in that formula, we have kinetic energy equals 1/2 mass times center of mass speed squared plus 1/2 moment of inertia with respect to center of mass times angular velocity squared. So here's the problem we're going to be doing in this video. We have here a fixed hemisphere, and we're going to start a solid sphere at the top of the hemisphere, release it from rest, and allow it to roll down the hemisphere. Now, at some point, that solid sphere will be rolling fast enough that it loses contact with the hemisphere, and we would like to know where that is. Now, to describe the position of that solid sphere as it rolls along the hemisphere, what we do is we draw a segment that goes from the center of the hemisphere to the center of the ball, and then we're going to say that that segment makes an angle theta with the vertical. So this angle theta here allows us to locate the solid sphere as it rolls down the hemisphere. So with that in mind, we're going to apply the extended object version of Newton's second law to that rolling sphere. Now, why we are going to do that, we will talk about in a moment. But for now, let's just go through our standard analysis using Newton's second law and force vectors and so forth. Remember that when we have this extended object version of Newton's second law, the acceleration that we are interested in is the center of mass acceleration. So what is the center of mass of that solid sphere doing? Well, what it is doing is that as the ball rolls down, that center of mass is tracing out a circle, or at least an arc of a circle, and the radius of that arc would be equal to the radius of the hemisphere, capital R, plus the radius of the ball, A. So with that, let's just do our force diagram on that sphere. Okay, so I'm going to just start by drawing that sphere out to the side. And we'll go ahead and put in our force vectors. So we'll have, as usual, gravity pointing straight down. We would have that normal force vector that the hemisphere exerts on the rolling sphere. Now I'm going to move that normal force vector up to the center of the sphere, like so. And then we would have static friction acting between the hemisphere and that rolling sphere, and that static friction force would point up along the tangential direction. Now we want to put in the acceleration. Now that center of mass is tracing out a circle, so we're going to need both tangential acceleration and radial acceleration. So let me put in that radial acceleration. So we have that radial acceleration pointing in towards the center. And usually we say that the magnitude of that would be the square of the speed divided by the radius. So let's use that formula. Here we are interested in the center of mass motion. So we use center of mass speed squared, and we divide by the radius of the circle it's moving on, which would be, as we see here, big R plus A. And then we also have the tangential acceleration because that center of mass would be getting faster as it rolls down the sphere. Now, I haven't mentioned this, but why are we doing this? Well, remember that the question was asking us to find the position at which the solid sphere loses contact with the hemisphere. Now, how do we know that the solid sphere is in contact with the hemisphere? Well, the way we know that is that we have a normal force acting between the solid sphere and the hemisphere. Once that normal force goes to zero, that tells us that the solid sphere is on the verge of losing contact with the hemisphere. Okay, so what we're going to do is solve for the magnitude of the normal force as a function of the position, where the position is given with the angle. So we solve for the normal force as a function of the angle theta here. We find the angle theta where the magnitude of the normal force goes to zero. And that angle where the magnitude of the normal force goes to zero, that gives us that last point just before the solid sphere loses contact with the hemisphere. Okay, so let's proceed. I'll put in magnitude of normal force N, magnitude of static friction force Fs, gravity mg. For our coordinate axes, I'm just going to put in coordinate axes along the radial and tangential directions. So let's say this is our radial direction here, and this is our tangential direction here. Now with that, we can set up our grid as usual. So I'm going to have gravitational force, normal force, static friction, acceleration, and then radial and tangential components for all of those. You can also check the geometry that the angle between the gravitational force and this radial direction here would be theta. That would be the same as this angle theta in here between the vertical and the segment joining the two centers. So with that, I can fill out the table. So for gravity, radial component minus mg cosine theta, tangential component mg sine theta. For normal force, it would have on the radial direction n, on the tangential direction 0, static friction minus Fs 0. And then for radial acceleration, it's pointing inward on the radial direction. So I have minus Vcm squared over R plus A. And then for the tangential component of the acceleration, I'm just going to put AT. We're not actually going to use that. Oops. Now that static friction is on the tangential direction. Sorry about that. Okay, so anyways, what we're interested in here is the normal force, where the normal force goes to zero. That's where that solid sphere is losing contact with the hemisphere. The normal force lives in the radial direction here. So let's apply Newton's second law in the radial direction. So now we're going to apply Newton's second law on the radial direction. So we are using the extended object version. So we have the sum of the external forces, radial components, equals mass times center of mass acceleration, radial component. So we're interested in the normal force here. So we're just going to read along that top row. Then we have minus mg cosine theta plus normal force equals, substituting into the other side, m times minus VCM squared over R plus A. So solve for the normal force. We have normal force equals mg cosine theta minus m VCM squared over R plus A. Okay, so we wanted to find the angle where the normal force goes to zero. And if we want to find the angle where the normal force goes to zero, what we would want is to have the normal force as a function of the angle. Now, in this first term here, we have the normal force related to the angle, but in this second term here, we don't have the angle. What we have instead is the center of mass speed. So what we would like to do is somehow relate the center of mass speed to the angular position. And then once we can do that, then we will fully have the normal force in terms of the angle so that we can solve the problem. Okay. So how can we get the center of mass speed in terms of the angle? Well, what we have to do is go back to the initial and final situation here and apply conservation of mechanical energy. Okay, so going back to initial and final situation, we're going to say that as the ball rolls down the sphere, gravitational potential energy is being converted to kinetic energy. So let's put our zero level down here. Okay, now we proceed as usual. We need expressions for initial kinetic energy, initial gravitational potential, final kinetic energy, and final gravitational potential. Okay, in the initial situation, nothing's moving, so kinetic energy is zero. Now, for gravitational potential energy of an extended object, we imagine that the entire object is compressed to the center of mass position. So think about taking that sphere and compressing it to its own center. And in the initial picture, that center is a distance r plus a over the zero level. So we're going to say that in the initial situation, the gravitational potential energy is mg times r plus a. Let's go to the final situation. In the final situation, look at the position of the center. Right? In the final situation, the center is here. Now you can see a right triangle in here where the hypotenuse is r plus a. So this distance here is going to be r plus a cosine theta. So the final gravitational potential energy is going to be mg r plus a cosine theta. Now, what about the final kinetic energy? Now, here's where it gets interesting. What we're going to do here is use this general formula for the final kinetic energy. I'm going to express this as 1/2 mass, center of mass speed squared, plus 1/2 moment of inertia with respect to center of mass, omega squared. Okay, here's where it gets interesting, right? If you remember what we were doing here with the normal force, what we want is an expression for the center of mass speed. Now, if you look at our final expression for kinetic energy, we have center of mass speed in there. It would be nice if we could somehow take the second term and express the second term in terms of the center of mass speed. So here's what we're going to do. So that ICM, that refers to the moment of inertia of the solid sphere for rotation about its center of mass. And that's a tabulated formula. It turns out to be 2/5 the mass times the radius squared. So that would be 2/5 mass times little a squared. And for the omega here, we're going to use the rolling condition. So remember the rolling condition. The rolling condition says that center of mass speed equals angular velocity times radius. So solving here for the angular velocity, that's going to become VCM over the radius. The radius of that little ball is A. Okay, let's work out what we have here. This is now going to become 1/2 mass of the little sphere times center of mass speed squared plus 1/2, then substituting 2/5 mass a squared, and then omega squared becomes VCM squared over a squared. When the dust settles, all of this becomes 1/2 plus 1/5. So 1/2 plus 1/5 is 7/10. You can see that the a squareds cancel here and here, and then we can pull out a common factor, m times VCM squared. Okay, so all of that work to show that in the final situation, the kinetic energy of that rolling solid sphere is 7/10 the mass times the center of mass speed squared. So now let's go ahead and apply conservation of mechanical energy. Okay, so we're going to use change in kinetic energy plus change in gravitational potential energy is equal to 0. All right, change in kinetic energy, that will be final minus initial. So 7/10 mass times center of mass speed squared. And then we have plus change in gravitational potential. So that's going to be final minus initial. Now notice with final and with final and initial, we can pull out mgr plus a. I'm going to have plus mg big R plus a. And then final minus initial. So we have cosine theta minus 1 equals 0. This is not pretty, but rearranging here, we get that the center of mass speed squared is equal to 10/7 g times r plus a times 1 minus cosine theta. So now we can combine this result here, which we got from Newton's second law, along with this result, which we got from using conservation of mechanical energy. So let me just box these. The number, let me call Newton's second law here 1, and conservation of mechanical energy 2. And we'll put 2 into 1. So I'm going to leave you with a couple algebra steps to fill in here, but you're going to end up with normal force equals 17/7 mg cosine theta minus 10/7 mg. Okay, so this gives us the So going back to the original figure here, this gives us the normal force acting between the hemisphere and the ball as a function of this angle in here as the ball is rolling down the hemisphere. Now, we were asked to find the angle here at which the sphere loses contact with the hemisphere. And that would occur when the normal force is equal to 0. So let's figure out now, when is the normal force equal to 0? So the ball loses contact when n equals 0. So we then have 0 equals all this stuff. And solving for theta, we get theta is equal to the inverse cosine of 10/17, which may be the only time you see that particular fraction in your entire education. And plug that into your calculator, and you get theta equals 54 degrees. Now, this is an experiment we can actually set up in the classroom. And somehow the ball always seems to lose contact before it gets to 54 degrees. So if anybody asks, we can set up this experiment in class. And if anyone can explain to me why the ball doesn't quite make it to be 54 degrees, I would be very impressed with that. Okay, so that is our first video.